Welcome. Today we are diving deep into fine-tuning large language models using Unsloth. If you have trained models in raw PyTorch or Hugging Face, you know the pain of VRAM limits and painfully slow training. Unsloth rewrites the core operations, like attention, ROPE, and cross-entropy loss, using highly optimized Triton kernels. By the end of this guide, you will understand the mathematical underpinnings and code-level intuition required to build highly efficient fine-tuning pipelines. Let's start with QLoRA. Fine-tuning an entire 8 billion parameter model requires massive VRAM for optimizer states and gradients. QLoRA solves this by freezing the base model and quantizing it to 4-bit normal float. The base weights are compressed, and we only inject small, trainable low-rank adapters. Mathematically, the forward pass replaces a standard dense projection with a quantized base matrix, B plus the product of two low-rank matrices, A and B. Unsloth accelerates this dequantization step directly in GPU SRAM. How do A and B work? Matrix A down projects the input from dimension D to a smaller rank R, and matrix B up projects it back to D. The scaling factor alpha determines how strongly to apply these adapter weights. If rank is 16 and alpha is 32, the adapter's influence is scaled by alpha over rank. Choosing the right rank is critical. Rank 8 or 16 is usually sufficient for style transfer, while complex reasoning tasks might require rank 64 or higher. Unsloth's real magic lies in its custom Triton kernels. Standard PyTorch operations execute sequentially, writing intermediate tensors back to VRAM. Unsloth fuses these operations. For example, instead of computing cross-entropy loss by casting logits to floaty32, computing softmax, and then the log loss, which causes massive memory spikes, Unsloth fuses these into a single step. It skips the intermediate VRAM write entirely, processing chunks directly in fast SRAM, which avoids catastrophic out-of-memory errors on consumer GPUs. Attention is an O of n squared bottleneck. Unsloth natively integrates flash attention 2, which optimizes the softmax computation over the QK transpose matrix by chunking and tiling. It also patches Rotary Positional Embeddings, or ROPE. ROPE injects positional information by rotating the queries and keys in the complex plane. Unsloth rederives the ROPE forward and backward passes to do in-place updates. This means your query and key states don't duplicate in memory, drastically accelerating the attention mechanism. When dealing with strict VRAM limits, large batch sizes are impossible. Gradient accumulation is the solution. Instead of updating weights every step, we process micro batches, sum the gradients, and step the optimizer after n micro batches. Unsloth ensures gradient accumulation doesn't degrade throughput by optimizing the reduction operations. If your target batch size is 128, and you can only fit 4 per device, you accumulate over 32 steps. The math is identical, but memory peaks are dramatically lower. For weights and activations, we utilize mixed precision. While the base model is in 4-bit, adapters and gradients are stored in bfloat16. Why bfloat16 instead of float16? Float16 has an 8-bit exponent, identically matching floaty32's dynamic range. This prevents numerical underflow during the backward pass without needing gradient scaling. Unsloth correctly routes these types under the hood, ensuring mathematical stability while keeping the memory footprint minimal. Before the forward pass, data preparation is crucial. LLMs expect tokens formatted with specific chat templates, like ChatML or Llama 3's instruct format. Unsloth provides incredibly fast tokenization utilities. We map our synthetic JSON data into prompt, user, and assistant blocks, appending end-of-sequence tokens. Critically, we mask the user prompts during loss computation. We only want the model to learn to generate the assistant's response, not to memorize the user's instructions. Let's walk through the forward pass. As a batch of token sequences enters, it hits the embedding layer, then moves through the transformer blocks. At each linear layer, Unsloth computes the 4-bit matrix multiplication alongside the LoRA adapter. The outputs are normalized and passed into the fused cross-entropy loss. Thanks to Triton, Unsloth avoids materializing the massive logit tensor in HBM memory, calculating the exact loss dynamically. The backward pass is where Unsloth pushes boundaries. Gradients flow backwards from the loss, but the base model weights are completely frozen. Unsloth's custom backward kernels calculate derivatives exclusively for the LoRA A and B matrices. By applying the chain rule, gradients for A and B are computed using the cached activations. Because the base weights W do not require gradients, we save immense amounts of memory, and Unsloth bypasses PyTorch's heavy autograd overhead. Learning rate scheduling controls the step size during gradient descent. For fine-tuning, a cosine decay with warm-up is standard. The warm-up phase linearly increases the learning rate, preventing large gradients from destabilizing the newly initialized LoRA matrices. Once peaked, the learning rate follows a cosine curve down to a minimum threshold. This ensures rapid learning initially, followed by fine-grained convergence as the model approaches a local minimum in the loss landscape. To apply these updates, we use an optimizer. PageAddendum W8-bit is highly recommended. Addem W tracks momentum and variance for every trainable parameter. Paged optimizers leverage unified memory. If VRAM fills up, optimizer states are temporarily offloaded to system RAM, preventing OM crashes. The 8-bit quantization of the optimizer states further reduces memory by 75% compared to floaty 32, with negligible impact on the final convergence of the model. A major challenge in fine-tuning is catastrophic forgetting. As the model adapts to your specific dataset, it overwrites its general knowledge. To mitigate this, keep your learning rate low and use a lower rank for your adapters. You can also mix in a fraction of generic instruction-following data with your domain-specific data, acting as a regularizer. Furthermore, techniques like weight decay and Addem penalize large weights in the LoRA matrices, forcing the model to retain foundational structures. Throughout training, saving checkpoints is vital. Unsloth integrates seamlessly with Hugging Face's trainer, but instead of saving a massive 16 GB model, you only save the LoRA adapters, which are typically under 100 megabytes. If you need a standalone model for deployment later, Unsloth supports model merging. It mathematically adds the LoRA weights into the base weights, yielding a new set of parameters, and exports the fully merged model. Monitoring evaluation metrics is how you detect overfitting. If training loss decreases but validation loss spikes, the model is memorizing the training data instead of generalizing. This is often seen if your dataset is too small or you train for too many epochs. Generally, 1 to 3 epochs is sufficient for LLM fine-tuning. Unsloth accelerates the evaluation loop as well, allowing frequent validation checks without significantly increasing the total runtime. Let's talk debugging. If you encounter an out-of-memory error, first reduce your micro-batch size. If it still fails, decrease the maximum sequence length. Unsloth's memory usage scales linearly with sequence lengths, but extreme contexts still require heavy VRAM. If your loss becomes NaN, it implies numerical instability. This happens if your learning rate is too high, or you aren't using BF16. Check your gradient clipping settings. Capping gradients at 1.0 prevents exploding values. Once training concludes, deployment is the next step. Unsloth allows you to push directly to the Hugging Face hub or export to specialized formats. For local inference on CPUs or MacBooks, export to GGUF format, which applies further spatial quantization. For high-throughput API servers, export to VLLM format. Unsloth handles the complex quantization mapping automatically, ensuring your fine-tuned model retains its accuracy while running on highly optimized inference engines. To summarize, Unsloth revolutionizes LLM fine-tuning by rewriting standard PyTorch kernels in Triton, optimizing ROP, attention, and cross-entropy loss. Combined with QLoRA, Beload 16, and PageAddendum W, you can train state-of-the-art models efficiently on consumer hardware. Master these mathematical intuitions and pipeline configurations, and you'll be well equipped to build incredible custom AI solutions. Happy fine-tuning!